Imagine a titanium device, cooled to -15 degrees, encased in multi-layered armor. It was given 32 minutes, it lasted 127, and in those 2 hours, the device transmitted something that changed our understanding, not only of Venus, but also of Earth's future, the first color photographs, the first sound from another planet, and data that sounds like a warning. This story is not about the destruction of a machine, it is a story about what it managed to tell before falling silent forever. October 1981, Baikonur. 2 identical rockets are being prepared for launch 5 days apart. Venera 13 and Venera 14 are the last hope of the Soviet space program to get answers from a planet that methodically destroyed everything that touched it. By this point, Venus had already earned its reputation. In 1970, Venus 7 became the first spacecraft to make a soft landing on another planet. It operated for 23 minutes, which was considered a triumph. Subsequent missions failed one after another. Some couldn't withstand the pressure, some couldn't withstand the temperature, and some couldn't withstand the acid clouds on approach. The engineers at the Lavochkin Research and Production Association knew what they were dealing with. They weren't designing a spacecraft, they were designing a machine for surviving hell. The body is made of titanium. Inside is a sealed capsule capable of withstanding pressure of 100 atmospheres. Between the outer shell and the instrument compartment is multi-layer thermal insulation. But that wasn't enough. At a temperature of 460 degrees, no insulation can last long. Heat seeps through, slowly but surely. The solution was found in phase transition physics. Cold accumulators, containers with lithium nitrate trihydrate, were placed inside the device. This salt has a unique property. When melted, it absorbs a huge amount of heat without raising its own temperature. As long as the salt melts, the electronics live. Before separating from the orbital module, the landing craft was cooled to -10 to 15 degrees. Every degree means extra seconds of operation on the surface. Every second means data. Estimated survival time, 32 minutes. On the 1st of March 1982, after 4 months of flight, Venera 13 entered the planet's atmosphere. The parachute opened at an altitude of 60 kilometers, then detached. It was useless in the lower layers of the Venusian atmosphere. The air density there is such that the spacecraft slows down on its own. At 3 hours and 57 minutes universal time, Venus 13 touched down at a speed of 7 to 8 meters per second. It was a hard landing, but the spacecraft was designed for it. The first data came in instantly. Outside temperature, 457 degrees Celsius. Pressure, 89 atmospheres. That's 4 times the temperature of an oven, and equivalent to the pressure at a depth of 900 meters in the Earth's oceans. The survival clock has begun its countdown. The first thing Venus 13 did after landing was to look around. Pyrotechnic charges blew off the protective covers from the camera lenses. One of the covers fell directly under the mechanical arm designed to measure soil density, an unfortunate accident, but one that did not interfere with the main task. The cameras came to life. What they saw was unlike anything on Earth, an orange-brown world, flat basalt slabs resembling ceramics cracked by heat. Between them, dark, fine-grained soil. No mountains on the horizon, no sky as we know it. Only a yellowish-orange haze so thick that it absorbs light several hundred meters away from the observer. The shadows are soft and blurred. Sunlight scatters in this atmosphere as if the entire planet were shrouded in thick fog. These were the first color photographs from the surface of another planet, a world that humanity finally saw with its own eyes. But Venus 13 didn't just watch, she listened. On board was the Groza 2 device, a complex for studying atmospheric phenomena that included a microphone. Its main task was to measure wind speed by analysing acoustic noise. A side effect was the first ever sound recording from the surface of another world. What did Venus 13 hear? Wind. Not a roar, not a whistle, more like a low, thick hum. The wind speed at the surface was only 0.3 to 0.5 meters per second, barely noticeable movement of air by Earth standards. But Venus's atmosphere is 90 times denser than Earth's. Even this faint breeze would feel like a stream of molasses flowing around the hull of the spacecraft. The recording also captures other sounds. A dull thud as the lens cap is removed, the metallic click of it falling to the ground, the grinding of the drilling mechanism biting into the rock, Each sound is an artifact of the machine's work, surrounded by this strange alien hum of a foreign atmosphere. 17 years later, a Mars rover will deliver a microphone to Mars, but Venus was first. While the cameras were filming and the microphone was recording, other instruments were working on the main scientific task, to understand what this planet is made of. The drilling rig collected soil samples from a depth of about 3 centimeters. The sample was placed in the sealed chamber of an X-ray fluorescence spectrometer, the only place inside the apparatus that was protected from the pressure and temperature of Venus. The analysis took several minutes. Result: basalt, a rock type almost identical to terrestrial oceanic basalts, characteristic of mid-ocean ridges on our planet. The landing site, the Phoebe region, turned out to be an ancient volcanic plain. This discovery carried with it an alarming implication. Basalt on Earth forms where magma rises from the mantle and solidifies. Venus, like Earth, was a geologically active planet. It may still be active today. The minutes passed. 32 minutes had elapsed and the device continued to operate. 40 minutes, an hour and a half. The lithium nitrate trihydrate melted, absorbing heat. The temperature inside the capsule slowly crept up, but the electronics held out. The engineers at the Deep Space Communication Center could not believe their eyes. 127 minutes, 2 hours and 7 minutes of continuous operation in conditions where lead flows like water. Then, silence. The salt had finished melting, the thermal barrier collapsed, the temperature inside jumped to critical levels in a matter of seconds. Venus 13 transmitted everything it could. Now it remains there forever, a monument to human stubbornness in the middle of a scorching desert. Venus wasn't always hell. That's the scariest part of the story. 4.5 billion years ago, when the solar system was just forming, Venus and Earth were almost identical. They were the same size. Venus's diameter is 95% of Earth's, similar mass, similar chemical composition. Both planets obtained water from the same sources, comets and asteroids that bombarded the young solar system, as well as from volcanic emissions from their own interiors. Climate modelling conducted by NASA scientists at the Goddard Institute for Space Studies reveals a striking picture. Venus may have had a shallow ocean and a temperate climate for 2 to 3 billion years. The surface temperature remained between 20 and 50 degrees Celsius. Cloud cover reflected excess solar radiation, preventing the planet from overheating. Think about it. 2 or 3 billion years of habitable conditions. Life on Earth began about 500 million years ago, if not sooner. Venus had plenty of time, and then something went wrong. About 700 million years ago, which is yesterday in geological terms, Venus experienced a catastrophe on a planetary scale. Scientists still argue about the exact mechanism, but the most likely scenario involves massive volcanism. Imagine an eruption that makes the Siberian traps on Earth, the very ones that destroyed 90% of life on our planet 252 million years ago, look like a local incident. Giant cracks tore open the crust of Venus. Lava flooded up to 80% of the surface, and along with the lava, colossal amounts of carbon dioxide poured into the atmosphere. On Earth, excess carbon dioxide is absorbed by the oceans and bound in rock through the silicate weathering cycle. Tectonic plates sink these rocks into the mantle, closing the carbon cycle. But on Venus, this mechanism has failed. The temperature began to rise, the oceans began to evaporate. Water vapor, a powerful greenhouse gas, intensified the warming. The temperature rose even more, evaporation accelerated. This is called the runaway greenhouse effect, a positive feedback loop that cannot be stopped once it has started. When the oceans had completely evaporated, water vapor rose into the upper layers of the atmosphere, where the sun's ultraviolet radiation split the water molecules into hydrogen and oxygen. The light hydrogen escaped into space forever. The oxygen bonded with surface rocks. The water disappeared. Without water, there was no one to absorb the carbon dioxide that continued to erupt from the bowels of the Earth. The atmosphere became denser and denser. The temperature rose and rose. Today, Venus's atmosphere consists of 96.5% carbon dioxide. Its surface pressure is 92 atmospheres. The temperature is 465 degrees Celsius, and it is practically the same across the entire planet, at the poles and at the equator, day and night. The atmosphere is so dense that it effectively redistributes heat. Paradox, Venus is closer to the Sun than Earth, but receives less solar energy. Its clouds reflect more than 70% of the incident light, much more than Earth's. If distance from the Sun were the only factor, Venus would be colder than Earth. But the greenhouse effect changed everything. The little heat that penetrates the clouds cannot escape back out. Venus is a greenhouse planet locked in from the inside forever. The data transmitted by Venera 13 helped scientists piece together this picture. The basalt composition of the soil indicated a volcanic past. Measurements of the atmospheric composition confirmed the dominance of carbon dioxide. The temperature profile showed the scale of the greenhouse effect. Venus told us how a planet almost identical to ours could turn into a graveyard planet. And in this story, we heard echoes of our own destiny. Venus is not just a neighbouring planet. Venus is a mirror. When scientists build models of Earth's climate change, they inevitably look to Venus. Not because we are in danger of turning into a scorching hell tomorrow, or in 100 years, but because Venus demonstrates an extreme case, the final destination that any planet with a dense atmosphere and greenhouse gases could theoretically reach. Consider the scale. Carbon dioxide in the Earth's atmosphere today is just over 0.04%. On Venus, it is 96.5%. That's a difference of 2,400 times. But the mechanism is the same. Carbon dioxide molecules allow sunlight to pass through, but trap heat radiation from the surface. The more molecules there are, the warmer the planet becomes. On Earth, this mechanism works to our advantage. Without the natural greenhouse effect, the average temperature of our planet would be minus 18 degrees Celsius instead of a comfortable plus 15. We live in a greenhouse, but a greenhouse with open windows. Venus shows what happens when the windows slam shut. NASA researchers have established a critical threshold. If a planet receives approximately 1 4/10 times more solar energy than Earth does in its orbit, an unstoppable greenhouse effect is triggered. Venus is located precisely in this zone. Earth is not there yet, but the Sun is slowly heating up. In 1 billion years, it will become 10% brighter, and our planet will be dangerously close to this threshold. 1 billion years is a long time, but there is a more pressing lesson to be learned. Venus lost its oceans not only because of its proximity to the Sun. The catastrophe was triggered by massive volcanism, the release of carbon dioxide on a scale that overwhelmed the planet's climate system. Similar events have occurred on Earth. The Siberian traps, 252 million years ago. The Deccan traps, 66 million years ago. Each time, there were mass extinctions and global climate shifts. But our planet coped. The oceans absorbed the excess carbon dioxide. Weathering of rocks bound it into carbonates. Life adapted, evolved, and filled the ecological niches that had become available. Why did Earth survive, but Venus did not? Perhaps it is because of water. Earth retained its oceans, which became a buffer mitigating climatic shocks. Venus lost its oceans and lost its protection. Perhaps it is due to plate tectonics. On Earth it works. On Venus, apparently it has stopped. Without tectonics, carbon does not return to the mantle but accumulates in the atmosphere. We do not yet know the exact answer. And this uncertainty is where the main lesson of Venus lies. We live on a planet with an exceptionally stable climate. Liquid water has existed on the Earth's surface for 4 billion years, a circumstance that may be extremely rare in the universe. We take this stability for granted. Venus reminds us that this is not a given. It is a fragile balance that can be disrupted. The data from Venus 13 became part of this understanding. Each measurement of temperature, pressure, and chemical composition is a piece of the puzzle. A puzzle about how planets live and how planets die. The world watched the results of the mission from different continents. American scientists analyzed Soviet data. The Cold War did not prevent the exchange of scientific information about Venus. European researchers built models. Later, the European Space Agency sent its own spacecraft, Venera Express, which operated in orbit from 2006 to 2014. Venus united humanity in a common question: how can we avoid repeating her fate? After Venus 13 and its twin, Venus 14, which incidentally lasted only 57 minutes, there was a long lull. For almost 40 years, no spacecraft touched the surface of this planet. It was too difficult, too expensive, too many other targets in the solar system, but Venus won't let go. In 2020, a group of astronomers led by Jane Greaves from Cardiff University announced the discovery of phosphine in the atmosphere of Venus, a gas produced on Earth by anaerobic microorganisms. The announcement caused a storm. Subsequent studies cast doubt on the results. Perhaps it was a data processing error, or perhaps it was a signal from ordinary sulfur dioxide. But in 2024, new observations detected phosphine again, and not only that, they also detected ammonia, another hydrogen compound that has no place in Venus's oxidizing atmosphere. What is it? Unknown chemistry, or something more? The cloud layer of Venus at an altitude of 50 to 60 kilometers is a strange place. The temperature there is quite Earth-like, from 0 to 50 degrees Celsius. The pressure is about 1 atmosphere. Yes, the clouds consist of droplets of concentrated sulfuric acid. But some Earth extremophiles survive in even more aggressive environments. Scientists estimate the probability of phosphine's biological origin at 10 to 20%. 80 to 90% is unknown chemistry that we do not yet understand. But even 10% is not zero. The irony is that if life exists on Venus, it may be older than life on Earth. 2 to 3 billion years of suitable conditions are enough for microorganisms to emerge. When the surface turned into hell, life could retreat into the clouds, the only remaining refuge, and now humanity is preparing to return. In 2029, NASA will launch the Da Vinci mission, a descent probe that will pass through the entire atmosphere of Venus, analysing its composition with unprecedented accuracy. If all goes well, the device will manage to take several photographs of the surface before it perishes. In the same year, Veritas will be launched, an orbital spacecraft equipped with radar that will create a detailed map of the surface of Venus. The European Space Agency is preparing the Envision mission with similar objectives. Meanwhile, NASA engineers are working on technologies that will change everything. Silicon carbide-based electronics capable of operating at 500 degrees without cooling. Thermal batteries that use Venusian heat itself as a source of energy. In laboratory settings that simulate the conditions on Venus, prototypes have already withstood 60 days of continuous operation. 60 days. Not minutes, days. The LLISSE project involves the creation of a small station weighing about 10 kilograms, capable of operating on the surface of Venus for 2 months or more. Not 127 minutes, 2 months. If this succeeds, we will be able to observe Venus for the first time not in fragments, instantaneous snapshots between the activation of the device and its destruction, but in dynamics. We will be able to see how the lighting changes during a Venusian day, which lasts 117 Earth days. We will be able to hear how the planet sounds at dawn and dusk, feel its rhythm. But that is the future. The present is silence. Venus 13 still stands there, in the Phoebe region, among basalt slabs and dark soil, its titanium hull blackened by heat, its cameras long since blinded, its microphone long since deafened, its drilling rig frozen forever in its last position. Over 40 years, the Venusian atmosphere has done its job. Sulfuric acid has corroded everything it could corrode. Temperature and pressure have deformed what the acid did not corrode. Perhaps all that remains of the spacecraft is a shapeless pile of metal, but the data remained. 127 minutes of information that changed our understanding of what happened to a planet that could have been our sister. Venus is not a distant threat. Venus is a reminder that space does not have to be hospitable, a reminder that climate stability is not a law of nature but a fortunate coincidence, a reminder that planets die, and that 127 minutes is an eternity if you know what questions to ask. Questions.